physics, is interesting, and more or less people started studying about nuclear physics. But before that, it was all atomic physics. In a way, we can also say that quantum mechanics first targeted to understand atoms, and then only it got into the nuclear. So that's very important. So whenever we are talking about an atomic topic of atomic physics, we are mostly concerned about the electrons, which is revolving around the nuclei, and we do know that the outermost electron will actually define the property of that particular atom. Looking into all those aspects, initially when the Rutherford model came in, it could explain certain things, but many things it could not explain. But Bohr model was a very successful model where we basically have the nuclei at the center, and it was said that the electrons will be revolving around the nuclei. So that's how it all started. And here, what we said is it was actually about orbit. So we call it as Bohr's orbit. But then later on, it was realized that it cannot be an orbit because the electron doesn't move in a fixed space. It basically has, a probabilistic space. So the probabilistic space is something like this, where the electrons might be anywhere in the shell. So it might be, a sphere. It's a sphere. Okay, this is what I'm representing here. So this idea of orbit was discarded, and people shifted to something which is actually called the orbital. And so the Bohr's model was actually followed by vector atom model. But it was not that Bohr model could not explain things. It could explain a lot of things. For example, the angular momentum. Now we know if we consider the angular momentum, okay, it's nothing but the linear momentum cross r, and if we just look into the direction, it will be 90-degree perpendicular, the direction of velocity and the distance. So you can just simply write it down as mvr. This angular momentum was considered to be an integral multiple of h divided by 2 pi. That was what actually was given by Bohr's model, where n starts from 1, 2, and so on. So it means that this quantity, which is the angular momentum, was also quantized as per Bohr model. So although Bohr did not shift into direct quantum mechanics, but whatever Bohr found out was coincidentally also supporting the idea of quantization of angular momentum. So that's very important. Okay? This is something which we already know. Apart from that, we also know about spectra, okay, and I think we have already discussed a bit about this. But as I said, spectra, in general, we can actually have an emission spectra and an absorption spectra. Absorption spectra. So whenever we are talking about an atom which is at the ground state, we are exciting it. So it is absorbing some radiation that will actually give rise to absorption spectra. But when we are having an atom and allowing it to relax, it's going to give out some radiation, which is nothing but the result of emission spectra. And based on this, we have also discussed about the hydrogen spectra. Okay, and this is something which is very important in chemistry. Hydrogen spectra, which is actually being studied. What happens here is that there are certain lines that we observe. Okay, we can easily remember it in this way: L, B, B, T. That's an easy way to remember. Okay, and we know that L stands for Lyman. This is something which is already there in your notes, so I think we can discuss it once. Balmer, P is Bastian, B is Bracket, and P is Fund. So P is silent, Fund. And the idea was simple that if you are basically having a number of energy levels, okay, there will be transitions of the atoms from the upper energy level to the lower energy level. So, for example, we have got an energy level n is equal to 1, n is equal to 2, n is equal to 3, n is equal to 4, and so on. If we have a transition of an atom, that means the energy gets lost. Okay, we are getting it in the form of a radiation which is coming out from n is equal to 2 to n is equal to 1, n is equal to 3 to n is equal to 1, n is equal to 4 to n is equal to 1. That will actually be lying in the Lyman series. On the other hand, if you have a transition from 3 to 2, 4 to 2, we are basically having to have something which is called the Balmer series. So it all depends on on which state it comes after transition. If it comes to 1, it is Lyman. If it's 2, Balmer. 3 is Bastian, and so on. Right. But then when there is a transition between two energy levels, let's say this is E2 and this is E1, it is coming from a higher energy level to a lower energy level. So it is E2 is greater than E1. So that means there is a difference between E2 and E1, E2 minus E1, and that energy difference is nothing but H. So this is the radiation, or this is the energy difference that is basically coming out because of this, and we can also write it down as hc divided by lambda. These formulas we obviously keep on using, so it will basically have a definite wavelength that is coming out. Based on this frequency and wavelength, we can say that what kind of radiation do we have. Okay, so if you're basically considering a visible range, it will be nothing but 400 to 700 nanometer, and there we are basically going to have a visible range. But most of the times, the radiation that is being given out is actually not lying in the visible range, because visible range is a very small part of that. Okay, so if you look into this, you see the Balmer series actually lies in the visible range. UV visible, a part of it is UV, a part of it is visible, and this is the range. If you consider the energy, if you know the energy, you can definitely find out what is the frequency, what is the wavelength using the formula. So Balmer series will lie between 650 to 365, and you know 400 to 700 is visible range. So some of the part will be actually in the visible range, and that is actually the reason that Balmer series was the first series which was observed when hydrogen spectra was studied. And later on, it came up with Lyman, Paschen, Brackett, and Pfund, because this was directly observable. So we have got Lyman, which lies in the UV range, and Paschen will be in the infrared range, and Brackett and Pfund will be in the mid infrared and far infrared region. So when we are talking about something as an infrared region, it means that we are going to talk about the uh, wavelength, okay, which should be greater than 700 nanometer, 800 nanometer, or something like that. So this was important. Okay, now these things was actually being explained by Bohr. So it was like Bohr could explain a part of quantum mechanics, but when it came up to multiple electron system, now hydrogen atom, in general, it has got just if you're basically just considering a hydrogen atom, okay, we are basically just considering a pool of protons. Okay, it's just a pool of protons. That means there is only one proton here. Pool of protons, one proton. In fact, in nuclear physics, if someone needs a beam of proton, they simply use hydrogen atom, because you don't have to do any kind of extraction. It is easily available, and you can actually use it as a pool of protons. So that is the uh, beauty of hydrogen atom. Okay, you just can consider it to be a proton. So that was just one proton that we are talking about. What about heavier atoms? For example, even if you consider something like deuterium, which has got a proton and a neutron, this spectra was very difficult to explain using the Bohr's idea. Even if you consider go to the heavier atoms, it becomes more and more difficult. So that is the main drawback of Bohr's model, and it could not explain those fine spectral lines of the hydrogen atom and so on. Okay, this history is very important, and that's why we are just looking into it. Okay, so that means that Bohr could not explain certain things, and then came up that what should be the next thing that should be studied if we want to understand what is the atomic structure all about. And that actually gave rise to something which is actually called as the vector atom model. So vector atom model is actually very interesting, and it's a very important part of the quantum model. Okay, and we are calling it as the vector atom model. So when Bohr actually gave his idea, he realized that the electron is revolving around the nucleus, which for the beginner it was obviously true. Later on, it was observed that we cannot really define the path, but definitely it's moving around the nucleus in an orbit. But then there was a problem. Bohr said that it was revolving around the nuclei, but he had no idea that the electron was also spinning along its own axis. Okay, a electron might be spinning in the this direction, or an electron might be spinning in this direction. So it has a spin of its own. At the same time, it is revolving. So when it is revolving, it is giving rise to something which we actually call as L, or the orbital quantum number. So this was our L, and we call it as orbital quantum number. Okay, but then if it is spinning around its own axis, this was actually having another quantum number, which is actually called the spin quantum number. So it means that the field that it produced, maybe the magnetic field, if we are talking about magnetic moment, is not only because of its orbital motion but also because of its spin motion. And that was the idea behind vectors atom model. Okay, since we are discussing this, we should also know a bit about quantum numbers, because if these things are clear, we can easily do our numericals. Okay, things won't be confusing. Quantum numbers, now there are four quantum numbers we have already seen in our quantum mechanics unit, when we were studying about the wave function and all. We know that if a particle is trapped in a box, the energy that it has is n square h square divided by 8 m a square. Now, in this particular case, the n value that we are talking about is nothing but the principal quantum number. So, this is one of the basic and most important quantum number that we were introduced to even in our lower classes. So, this is the principal quantum number that we have, and this principal quantum number actually defines the energy. It is talking about the energy of the system. So this is the first quantum number that we should actually know. So let me write it down as number one. The second quantum number is obviously the orbital quantum number. The orbital quantum number. Orbital quantum number, which is actually denoted by L. Okay, and n and L are very much connected. If n is equal to 1, L is equal to 0. If n is equal to 2, L is equal to 0, 1. Now this L value, what does it define? It actually defines the shape of the orbital. Shape of the orbital. Okay. So this L is the orbital quantum number defining the shape of the orbital, and that's why when L is equal to 0, we basically call it as the S state. When L is equal to 1, we call it as the P state, and so on. And when it is 0, the shape of the orbital is spherical. It simply means that the electron will be in a spherical region. But when we are talking about p orbital, it will be in the dumbbell shape. So the electrons will be somewhere here. There won't be any electron here or here. Not possible. Okay. So that is the second quantum number that we know. What about the third quantum number? The third quantum number is actually the magnetic quantum number. The magnetic quantum number. These things are important to understand, quantum mechanics. And the magnetic quantum number is usually denoted by ms. Okay, and if we just consider it, we know that if we are basically having a value, the magnetic quantum number actually will depend on the value of s. Magnetic quantum number will start from minus l, and then it will pass through 0, and then it will be plus l. All these are integer values. So that means if we are basically considering, let's say, L is equal to 1, then the magnetic quantum number ms would be equal to minus 1, 0, and 1. Now L is equal to 1 means we are considering it the dumbbell shape. But then this minus 1 will represent the dumbbell shape along the x-axis. Let's say we can write it down as px. We can write it down as px. This will actually represent the y orbital. So this is py, and this will actually represent along the z-axis. This is pz. So that means the magnetic quantum number is actually giving me the idea about the orientation. Orientation. Okay, and of course the fourth one is the spin quantum number. These are the four quantum numbers that are most important. It's not that these are the only four. We have got other quantum numbers as well when we talk about nuclear physics, baryon number, lepton number, and so on. Okay, but we are not going to discuss that. Spin quantum number, this is ml, sorry, this is not ms, this is ml. ml, yeah. Spin quantum number is denoted as ms, and we know it can be an upspin plus half or a downspin represented as minus half. Upspin plus half, downspin minus half. And this will also represent the quantum number. So that means that if I have an energy state, and if you consider the Pauli's exclusion principle, we can actually have two electrons in the ground state, but the condition is both of them should not have all the quantum numbers same. So there are four quantum numbers as of we know now: n, l, ml, and ms. Even if n, l, ml are same, ms can have two values, half and minus half. So that means these two quantum numbers are not same. They can be taken by two electrons and they can be in the same energy state, and that is the idea behind Pauli's exclusion principle. So I think we did a quick recap of whatever we know. Okay, so this is important because based on that we actually have the problems and numerical problem that you have in your tutorial. At the same time, we're also going to discuss Stern Gerlach experiment because I think that is also important. Just a sec. So if you just look into one question that you have in the tutorial, just checking this. Although your questions are not very straightforward, so we have to be very careful. Let's just look into this particular question. Okay, and this is actually simple. Whatever we discussed just now, based on that, we can actually do it. Okay, it's not very complicated. Anyway, let me not skip it. Let's just read the question once. The question says a one-dimensional potential well has a width of 1 nanometer and contains 10 electrons. So it is basically a one-dimensional potential well. The width is given and it has got 10 electrons. So let's just look into this from an understanding point of view. So what happens is that if you are considering a potential well, and we are going to use obviously the Pauli's exclusion principle here, and let me draw some energy levels here. Let's say this is 2, 3, 4, 5, 6, and so on. And this is a potential well, so that means we are saying that the electron cannot escape it, and there are 10 electrons in this potential well. Now the problem is that if we are considering the lower level 1, this is 2, this is 3, 4, 5, 6, 7. The electrons can occupy the state using the Pauli exclusion principle, one spin up, one spin down. So one spin up, one spin down, one spin up. Here will be 2. So it's not that all the electrons will be in the ground state. It has to be in the upper energy level as well, because according to Pauli's exclusion principle we have all the electrons in the ground state because they have similar quantum numbers. So here also this is 1, this is 2, so we have written 6, 7, 8, 9, 10. So we have accommodated 10 electrons. Okay, and this is the situation that we have right now. So the thing is, it has got a width which is given, and there are 10 electrons here. If you look into this question, the system of electron width is 1 nanometer. Okay, the system of electron has a minimum total energy possible. So minimum total energy is this. This is the minimum total energy state possible. All the electrons cannot be in the ground state because of the principle. So that means up to the fifth state it would be occupied, and this is the minimum energy state that is possible for this, and 1 nanometer width. So this is the situation right now. What is the least energy in EV a photon must have in order to excite a ground state n is equal to 1 electron in this system to the lowest higher state it can occupy? So it's simple. It says that what should be the energy of a photon. That means I want to allow a photon to be incident here so that one of these electrons, okay, either one of these electron, let's assume this electron, gets excited to the next excited state. Now the next excited state is 2, where there are already two electrons which are sitting. So that means it is not possible that this electron will, it cannot be there because of Pauli's exclusion principle. So accordingly, 3 cannot be there, 4 cannot be there, 5 cannot be there. So the only possibility is that the electron can go and sit in the sixth energy level. So this electron that we are seeing can jump to the next possible energy state, which will actually be the sixth state. So if we actually want to do our calculation of the electron which is at the lowest energy level, that is at the ground state, we can simply use the formula n square h square by 8 m a square. Now I said n is equal to 1, right? So that means we can just simply write it down as 1 square. So that's 1. So it's square. So I can just simply write it down as 10 to the power 8. So that means the order would be nothing but 10 to the power minus 68. And of course, we want to convert it into EV. So why not? Into 1.6 into 10 to the power minus 90. So the order is 10 to the power minus 68 plus 31 plus 36 plus 19, not 36, 80. Not 36, it's 80. Okay. And this side we can actually calculate these values. Let's just do it a quick check of these values. So it's mistake 6.6 into 6.6 is this. You can also do the calculations so that we confirm this. Divided by 9.1 is equal to this, divided by 1.6. So that's 0.37, so that's fine. It is 0.37 into 10 to the power j. So this is 0.37 into 10 to the power minus 68, 31, 19 is 50, 50 and 18, right? It's 68. So that's 10 to the power 0. So we're getting it to be 0.37. So that means our answer would be 35 into 0.37. So that's there already into 35. So getting 13.08. I believe that's the answer that is given, 13.08 E. Let's check the PDF. 13.08. Okay, so it's okay. They might have taken more decimal places. We have not done that. Maybe each they have taken more decimal places. That's fine. Okay. The next problem, it talks about Stern-Gerlach experiment. But before that, I think Stern-Gerlach experiment theory is very important. And let's do a quick recap of that, because all the formulas that are being used here is actually belonging to that particular theory, okay, which is there. So let's just do a quick understanding of Stern-Gerlach experiment. Stern-Gerlach experiment. So, whatever we understood in vector atom model, we can say that Stern-Gerlach experiment is actually an application of that. Okay, what happens is, if we are looking into the features of vector atom model, there are two features there. There are two features. Okay, one is the spinning electron. That is very important. Spinning electron, as I said, that when we are talking about the Bohr model, we only have the electrons revolving around the nucleus, but then vector atom model considered that the electron is actually spinning on its own axis as well. Okay, at the same time we also have a feature like space quantization. Space quantization. Space quantization, it simply means that if you are basically considering any atom or electron, basically it will basically have related to it three quantum numbers. One is L, describing its energy, one is L, describing its shape, and one is Mn, describing its orientation. So you are looking into the space quantization part. So in fact, it is not a 2D picture, it's in fact a 3D picture here. and all these three dimensions are actually defined by these parameters. Okay, so that's very important. Now if we want to verify these features of the vector atom model, a very good experiment is nothing but the Stern-Gerlach experiment, which actually explains the vector atom model. What actually he did, the scientists, what they did was they actually have taken a closed enclosure, okay, and they have put some silver in it, silver atom, okay, and that enclosure is nothing but an oven, okay, it is an oven, and the silver atom was actually coming out of this, okay, and normal experiments we put slits, so the slit was there, and then this particular silver atom was allowed to pass through a the beam of atom was allowed to pass through a non-uniform magnetic field. This may be considered as a non-uniform magnetic field. Okay, I'll tell you how. And as soon as it passed through this non-uniform magnetic field, the rays or the beam of atom actually started deviating. So it deviated in the upward direction, it also deviated in the downward direction, and so on. So that is the basic idea behind Stern-Gerlach experiment. So this is actually an oven, and inside there was a bed of silver, and when this was heated, this silver atom got released, okay, and it passed through a slit which made it parallel, and then it was passing through a non-uniform magnetic field. So this magnetic field that we have is non-uniform, and as soon as it passed through this, it got deviated in different directions. Okay, it got deviated in different directions, and we can consider that that is actually along the z-axis. So this was the actual setup of Stern-Gerlach experiment. If you read the theory for this, it's not very complicated. This is the simple setup that we have, and you also understand that this will be actually a non-uniform magnetic field, because if you're basically considering the magnetic poles, let's say something like this, we'll see that the since this is pointed, as we go from this part to this part, we'll see that the lines of force come closer to each other. So here it is evenly distributed, here it is coming closer to each other. That simply means that this is actually a non-uniform magnetic field. Okay, so this is the idea that Stern-Gerlach used, or this is the setup that was actually used by Stern and Gerlach. And the atoms that were actually coming out of the nuclei, it was actually neutral. Okay, so the silver atoms, okay, that we are considering, these formulas are important, and this logic is also important, which can be used in numerical. So if any kind of numericals are given to you based on Stern-Gerlach experiment, this is more or less the story here. Okay, are neutral. So if they are neutral, that means we obviously know that Q is equal to 0. There is no charge as such. Now if there is a magnetic field, and if this is neutral, and we are saying that this does not have charge, why does it deflect? That is the question, right? That is a very important question that we need to know. So if they are neutral, we know that, if you recall Lorentz force, we are just having magnetic field here, no electric field. So we can just consider the magnetic part of that Lorentz force, and this is nothing but Q V B sine theta. That was a Lorentz force. But since Q is 0, this part is actually 0. That means it does not show any kind of deflection. Okay. So what is the net force that is acting? So the force that is acting, because of which there is a deflection, is this. Okay. So we will derive this. So the net force acting is this value. So this force is acting along the z-axis, because we are saying it is getting deflected along the z-axis. And that is actually what is happening. This is del Bz divided by del Z into the magnetic moment Z. Magnetic moment we denote it by mu L Z. So this is the net force acting on it, which is the formula that is being used. The question is, how do we arrive at this formula? So this is something which we are going to do. But let me tell you before that something about gradient. Okay, Stern-Gerlach experiment is a very long experiment. Let's try to understand this anyway. Let's talk about something which you call as gradient first. So if you're saying that something is placed at some height, some mass is placed at some height, this is the mass, and after some time we're moving it here, and it remains at the same height. That means the potential energy does not change. The potential energy is here, the potential energy is here, both are same because they are at the same height. It doesn't depend on time. So that means there is no change in potential energy. That means the gradient is zero. But on the other hand, if you're basically considering, let's say, something like this, an elevated space, and you are having the mass here, and it after some time it changes here. That means the height is changing. It was after this initially it was here, and then it went to a larger height. So that means there is a potential energy gradient. So that's the first concept that we should know. If you look into this term del del Z, this is actually representing that gradient. If you're considering a non-uniform magnetic field, it is uniform here, it is non-uniform here. So, there is a change in the strength of the magnetic field. So that means we can say there is a change in the gradient. Okay. So let's just look into it, how exactly this relation was derived. The first thing that we should know, a very important concept, is that electron, behave as a magnetic dipole. That's very important concept. Behave as magnetic dipole. Now, why do we say that? The idea is simple because if you're considering the electron revolving or spinning or whatever, we basically consider that it's a charge and it is revolving, okay, or orbiting. So if you're basically considering that electron is a negative charge which is actually orbiting around the nucleus, and if you recall this concept that if there is a charge which is actually revolving, it is acting like a dipole. So we can consider it to be a combination of north pole and south pole. So if we are saying that the electron is revolving around the nuclei in the anti-clockwise direction, it is representing a north pole. And if you look into this electron from behind, it will be giving us an assumption that it is revolving in the clockwise direction. All right, that's how nature works. So that means this will be representing the south pole. So that means electron revolving around the nuclei is behaving as a magnetic dipole because it has got a north pole and a south pole according to the logic, right? So that's why we consider it to be a magnetic dipole. And then there was a concept which we did in your class 11 or 12, I think, that if we are basically having a magnetic dipole and there is a magnetic field, what is the force acting on it or torque acting on it. Based on that, you can also calculate what is its potential energy. So the potential energy of this particular dipole, let's represent it as U, is nothing but minus mu L bar dot B bar. This is the potential energy. So the B bar is the magnetic field that it is creating, and of course mu L is nothing but the dipole moment. Dipole moment, I hope you know. You take any of the charges or any of the strength of the field, rather the strength of the north pole or the south pole, and multiply it with the distance between them. So this is the general formula for the potential energy. Okay, and this mu L, okay, is actually representing something which we call as the magnetic moment. We also call it a magnetic moment. So that's an important term. It obviously tells me about the strength of the field that it is actually creating. Now, if you're basically considering a 3D picture, which is more realistic, this magnetic moment will basically have a x component along the x direction, right? It will also have a y component, and it will have the z component along the y direction. That will write down 0. Okay. Similarly, if you're basically considering the magnetic field, we can say that this will basically have the x direction, the y direction, the z direction. Okay. But we are applying a magnetic field according to our own will, and we are applying the magnetic field along the z direction. So that means there is no magnetic field along the y direction or the z direction because we are controlling this field. Okay, so that means we can just simply write it down to be bz. Okay, right? Now, if I take the dot product of mu L and B dot product, right? So that means I'll take this BZK. We have just got BZ Z component for the magnetic field. If I take K dot I, it is 0. K dot J, it is 0. But K dot K will actually give me a value, right? So that means I can simply write it down as mu L Z dot BZ. Okay, so we can just simply write it down in this form, so that's possible. Okay, even there is no meaning of writing down dot because we have already taken the dot product, so maybe you can take it as multiplication. This is not cross product as well, just the multiplication. So we can take this as number, so that's very important. So we have taken the relation and we have it, and I think now it's almost done because we want to find out what is the force which is acting. We want to find out what is the force that is acting along the z direction. And if you recall, whenever we are writing down force, we can actually directly connect it with the potential energy. Force, okay. So what is this? This is potential energy, right? So there is a minus sign. Therefore, we can say that potential energy is equal to minus mu L Z B Z. Okay, so let's take this as 2 and not this as 2. Let's write down the potential energy as 2. If you recall again now the definition of force, this was actually nothing but minus delta V, where V is the potential. So let's represent it as U because U we have seen it as potential here. So minus delta means we are talking about the gradient. So it would be nothing but minus of I del x plus j del y plus k del z. Of course, there is a cap with ij and k. And this would be nothing but minus mu l z b z. So if I take this, this minus and this minus will get cancelled out. It will be plus. Just del z makes sense. Other things are more or less zero because we only have the z component. Mu Lz is the magnetic moment along the z direction. That's a constant, so I can just take it out of the differentiation sign. This is mu Lz into this would be nothing but del z of the z. That's the force that we have when we are basically having the electron. What is the most important thing here? The most important thing is that we ignored the fact that electron will act as a magnetic dipole in earlier theories, but we cannot do that. We have to realize that electrons are nothing but acting as dipoles, which is actually having a magnetic field of its own, as a result of which it is definitely going to experience a force whenever it is allowed to pass through a magnetic field, even if it is chargeless, because when it is revolving, if it's a neutral atom, we have electrons which is revolving, so it is creating a magnetic field of its own, because of which there is a deflection. So if q is 0, still there will be deflection. So that's the beauty of this particular experiment. Okay, it's still not done because the question is how much does it deflect, what is the distance by which it gets deflected. That's very important. From the center, what is the distance by which it gets deflected. So if you want to do that, that is also simple because from this particular relation, we know, let me write it down here, we have that this F force is actually proportional to whatever is the magnetic moment. So if there are more electrons, there will be more magnetic moment, and that means the force of deflection would be more. Okay, let's mark this as number A. Now, if you want to know how much is the deflection, we can simply use the formula S is equal to ut plus half at square, simple kinematics. So Sz is equal to ut plus half at square. U is the initial velocity, not the potential, right? But initial velocity is 0. Let's say it starts from rest, so it is 0. So this result is only half at square. Acceleration from the z-axis, so let me write it down as az t square. Okay, so that means this sz or deflection that we actually are having is directly proportional to the acceleration along the z-axis. Let's mark this as number B. And one more thing finally, which we know is, but whatever may be the acceleration, okay, which actually depend on what is the force that is being applied, what is the force that is acting on it. More the force, more would be the acceleration. That is something which you already know from our basics. So fz, this is c. So we've got three relations here, a, b and c. Okay, and from this what we can conclude is, let me write it here, a, b, c implies that this deflection sz is directly proportional to the acceleration Az, which in turn is proportional to the force that is being applied Fz, and this force is directly proportional to whatever is the magnetic moment that we have. So that means that the deflection that we have is directly proportional to the magnetic moment. This is a very important conclusion, because sometimes it's a bit confusing that why does it deflect more if the magnetic moment is more. This is the reason we have concluded from this. So this is more or less the theory of Stern-Gerlach experiment, which tells me that why does an atom which is actually neutral deflects whenever there is an atomic or magnetic field which is non-uniform in nature. This actually talks about the spinning electron and space quantization. Okay.